Good morning. Good morning, everyone. Welcome to our webinar. For those of you who have been on some of our webinars in the past, this is going to be a little different. We're not going to sit and talk for an hour about what we think is important. We're going to take some questions and hopefully give you some answers. We've assembled some smart guys here and me, and we're going to go through questions that have been already submitted, and then we will get to any questions you have. So if you hear anything or you want further clarification, think about it and hold on to it. So we've got a number of people here today that have a variety of experience, decades of experience around the world, and we'll go through them. Just a quick introduction to everyone. We'll do that. Then we'll go through the pre-submitted questions, and then we'll answer any questions you have live. If you have any issues during the broadcast, you've got a button on your phone or on your control panel to raise your hand. And if you raise your hand, then Tim Irwin, who's my associate and working behind the scenes, he will direct you to wait till the end if you have a question. If you have a problem, just use the chat box and type it into the chat box, and he'll answer you. So, but the actual question submission we'd rather do live at the end. So, without further ado, we'll move on. Our first panelist is Stuart Aird. He's the Global Product Manager for EA Technologies full-time partial discharge monitoring. But in addition to that, he's been doing hands-on partial discharge testing, both online and offline, all over the world. He's been in Singapore, he's been in Australia, he's been in the US, lived in the US for a year doing online and offline testing, and he's worked all over Europe. So he's got a lot of hands-on practical experience and can help you out, as well as being the lead support engineer for EA's test equipment. So he gets all the strange questions that people ask. He does lots of trainings and has been in front of a lot of customers. So he should have a good handle on most of the questions you can come up with. Next on our list is Mr. Tim Conley. He's with Western Electrical Services. He's a NETA level 4, which is not an easy level to get to. And he's been doing a lot more than just partial discharge, but he's been doing testing, maintenance, repair, retrofit all over North America. Before that, he spent 23 years in submarines working with the nuclear power and nuclear power at Exxon. So he went from shipborne to land-based nuclear power, and spent some time with Eaton Electrical, and a brief stint with the U.S. Army Corps of Engineers. Now he's back to Western Electrical Services. So he's done a lot. Been in the field, seen the problems, worked on both the measurement and detection of partial discharge, but also the repair and diagnosis, which is often a difficult part as well. So he's got a lot of experience with these sorts of issues. Our third panelist is Jeff Porlingam, who is with Leading Edge Sales in Calgary. Despite him being a salesman, he's got some technical chops too. He spent quite a bit of time at Magnafor Engineering, where he was in charge of electrical engineering, diagnostics, hands-on work with testing and commissioning of high voltage systems. And before then, he spent time with General Electric working on their protective relaying, and that was more in a product design role and product specification role. And he's got over 20 years experience and is a registered professional engineer, which is not an easy thing to get. Last and maybe least is myself. I've been in the power industry for 32 years. I've been working with partial discharge testing for the last 7, mainly online testing. I don't have a lot of offline testing experience, but I've been all over North and South America doing installation of monitors, and I write a lot of articles and do a lot of presentations. So I've been asked a lot of questions by people when I'm up on the podium, and I've got some answers. Plus, I've got a team to back me up here, so I'm good. I'm happy this time. I don't have to do all the talking. I got some smart people to answer hard questions. So, like I said, at the end of the presentation, you can either type your question in, or if you want to say it out loud, you can raise your hand and Tim will let you in. So first we'll go to the questions that have been submitted ahead of time. Okay, so the first question is, where and how do you find most partial discharge deficiencies? And I'll turn that over to Tim Conley.
There's a couple different methods I primarily have utilized in my partial discharge detection. One is obviously the transient earth voltage detection method. The other one is ultrasonic. And primarily, most of my deficiencies I have found have been surface generated partial discharge events. And in doing so, that is used where I've used the ultrasonic detection method. And what is occurring is that you have some sort of product, something that is starting to break down the insulation either from phase to ground or phase to phase. Bill, have you got anything you want to add on to that?
No, but yeah, ultrasonic is the best method for detecting surface discharge, and that's where we find most of our most discharge is found through ultrasonic.
The picture that's attached to this particular one actually was discovered down in Florida. It was exposed to a combination of chemical attack and also just environmental conditions with extreme humidity, extreme temperatures, and it started to break down and was discovered.
Okay, move on to the next question. All right, so using ultrasonic, related to the last question, I hear a lot of things, and they could either be corona or surface PD. And I'll just describe that a little bit. Corona is a subset of surface partial discharge, where the discharge is, instead of tracking along the surface of the insulator, is discharging directly to air. So you'll find that very often with EHV systems and air insulated systems that may be up on poles and structures. And surface discharge is a much more serious situation where it occurs on the surface of the insulator and degrades the insulator. So how do I tell the difference? Jeff, you want to take that one?
Okay, so yeah, it is a bit tricky to determine whether it's corona or PD, especially if you're using a traditional method like listening to the PD. But you know, especially if you're looking at outdoor gears, substations, and if you're using some of the dishes that are used typically to detect partial discharge, what you're going to see is, you know, they will both sound pretty much the same. One way of determining is if the conductor, especially the insulators, if you hear sort of PD or corona, you will hear intensively in closer to the where the electrodes meet the insulation. But if you scan along the line towards the ground, that noise will diminish. And that's one way of saying, well, that's closer to the conductor. Most probably it's corona. But in this day and age, with the new technologies, using especially if you start looking at the phase resolve plot, it's a lot more easier to differentiate. Corona, typically what you see is sort of unipolar or uneven compared to the surface partial discharge, which is sort of an even bipolar and a separation of 180 degrees shift. You can see that picture in the presentation. So that's one way of determining whether it's actually a PD or corona, surface PD or corona. Anything you guys want to add?
No.
Okay, we'll move on to the next question.
Oh, just excuse me, just to add, you can also use there's also ultra high frequency sensors. They seem to be a better way of, especially if you are in an outdoor environment, it's a better way of separating corona and surface PD. They are, because corona and surface PD, they are in a totally different frequency slots. Ultra high frequency sensors are used for that purpose. It's easy to separate corona from surface PD.
Yeah, that's right, Jeff. But if you're using a UHF sensing method, corona tends to roll off at an upper frequency around 300 or 400 megahertz, and surface PD goes well above 1 gigahertz. So if you're looking at band above 400, say, and below 1 gigahertz, you can pick up surface PD and know that it's not corona. So you need to filter that down. But if you filter that down, you can definitely tell that it's not corona. Okay, so why can I take a TEV reading, a transient earth voltage reading, and it's really low, but I can still hear ultrasonic or even audio? It's very loud in the ultrasonic or audio band. Why am I getting such a low TEV reading? Stuart, you want to address that one?
Yep. So, for transient earth voltages, we actually need to the discharge creates some electromagnetic emissions, and they induce a voltage into the steelwork. But so in an internal void, the amplitude of those signals are quite large from respectively compared to ultrasonic. So
can you speak up a little bit, Stuart?
I'm sorry. Yeah, so if you've got an internal void, there'll be very high amplitude electromagnetic emissions from those, and they induce a good size transient earth voltage into the steelwork on our switchgear. So for an internal void, we will get a high amplitude but a low repetition rate of these electromagnetic emissions. But for an ultrasonic surface discharge, you get lots more of the actual discharges, but they're a lot lower amplitude, so they don't create a high enough emission to create a TEV voltage into the steelwork around the switchgear. So quite often, we'll catch a ultrasonic. We can hear ultrasonic audibly, or and even audibly coming out of this compartment. But there's very, very low transient earth voltage signals on the surface of the switchgear. So it's very important that we do both surveys whilst doing our partial discharge surveys to ensure that we're picking up internal and ultrasonic. We can't do one survey without the other survey. Anything else?
Okay, great. Let's move on to the next question. Is PD testing destructive? And I get to answer this one. It's an easy question. We get asked this question all the time. It's a concern to people that I do this test and now I've caused myself a problem. And this is a bit of a leftover from the old school where people, before they knew about the space charge problem, they do high pot tests and the cable would pass the high pot test and then they'd energize it and it would blow up in the first half cycle. Not going to spend time on that now, but that's put a bad taste in people's mouths about testing cables. And with offline PD testing, you will often test above the nominal line voltage. So you might test as high as 1.7 times the nominal line voltage. And people will say, well, if the cable can't withstand that, it would fail. And that's true. But if a cable can't withstand 1.7 times its nominal rating, then it was probably weakened and about to fail anyway. So with offline testing, yes, it is possible, but it's probably finding a problem that you really had. Online testing is purely all listening. You're not connecting in most cases to the conductors. You're certainly not injecting anything. So there's no way online testing could ever hurt a cable. One of you guys with more offline testing experience want to chime in?
Predominantly, my testing has been done online. Customers are apprehensive from the standpoint of bringing you in and now you found a problem, how do we deal with it? And that's how you have to approach your customers from a technician standpoint of, we've now found a problem and we need to make or create a flow path for determining the location and then the corrective actions necessary.
Okay.
Yeah.
All right, great. Let's move on. Okay, so how do you isolate or localize partial discharge to a particular component? Always a problem. Tim?
Oh, very much so. This is very challenging because you're on the outside of the equipment initially. If you take a look at several slides back when we were doing our introductions, it actually shows me in the back of some switchgear, right? That switchgear theoretically would be either in service or out of service, and that. But to localize a fault, you have to make a decision of how are you going to try to locate it. First off, our normal detection methods, whether we're using the transient earth voltage detection method or doing an ultrasonic method, you initially know you have a problem. Yes, there's a problem inside, but how do you localize it? And in those situations, you have to make a determination, especially with NFPA 70E requirements, where they want you to establish an electrically safe work environment and isolating power, turning it off, and going in, and in some cases either doing insulation resistance testing, visually inspection. Now, in doing localized cable testing, one of the first things that I do when I open up the rear switchgear, yes, it is energized. Yes, I've got my energized electrical work permit. Everybody understands the hazards associated with what I'm doing. But when I open up the rear of the switchgear to access cables, I will do a full scan of the rear of the switchboard with both transient earth voltage detection and also ultrasonic. This is where I found a number of problems with so far as the surface partial discharge detection. And the nice thing is we have, I don't know if we have a picture of it maybe later on, but we have it's a parabolic microphone arrangement, which allows us to really focus in down to very point localization on insulators. And I have come up with a number of fault locations simply using the parabolic microphone associated with the device, the equipment. And there's a number of different pieces of equipment out there that's used, but again, it can be done online or offline. If you're going to do it offline, you're going to insert your own over potential signal with a high pot, AC high pot, and that will allow you to localize across various insulators if you're not able to detect it visually. Anybody want to add to that one?
Yeah, what I also think is adding to what you said about the parabolic dish. One good thing about that is that even you can, once you open the door, you can stay in a safe distance depending on the size of the space that's allowed. You can stay further from the switchgear about 2, 3, 4 meters and still use that parabolic dish or the sensor to locate where the source of PD.
Absolutely. And in one case in particular, it was at a waste treatment facility. I found literally what could have been a severe showstopper. It had faulted out. It was nearly ready to fault out. I brought the manager over, showed him exactly what the problem was, allowed him to listen to what was going on, and pinpointed down to the exact location. And immediately phone calls were made, power was shifted over, and they shut that section of switchgear down. He looked at me and he said, honest to God, what you found has now just paid for having you come in. Simply because of, had this portion of the waste treatment facility had a fault between the EPA fines that would have occurred and the damage to the components downstream would have just been astronomically expensive.
That's very true, Tim. It's always good to be able to show the customer or the user, the owner, specifically what's going on, because there are still people that think partial discharge is voodoo. So proving it is always helpful. Okay, another one for Tim. So I'm inside, I've got my cable tests. My cables are inside, the ground straps are inside the high voltage compartment. This applies to ANSI type gear. IEC gear is lucky in that they use glands and have the ground straps outside the compartment. But how can I safely do these tests if I've got to get inside the compartment?
Obviously, there's a number of different methods. One is a permanent installation. Have a controlled shutdown outage and plan. And first off, start with permanently installed equipment. I can't stress it enough. That is your best route. There are a number of manufacturers out there. I'm, of course, an independent testing organization, and I do retrofits. So I strongly recommend, from a cable standpoint and from a permanently installed installation monitoring, go with do your product reviews and do a permanent installation. Much, much safer. This picture here shows hot stick applications. And again, that is the next method where you can safely access from a few feet back, and that to get onto the cable shields. You can't always do that. And last but not least is you're literally opening up the rear of the switch gear, walking up to it, and accessing the circuit's cable shields to install temporary radio frequency CTs in order to gather your cable data. And again, I can't stress this enough. Look at NFPA 70E. These are things, this is considered testing. So, but you're going to want to have your energized electrical work permit. Make sure everybody understands what the technician is doing while they're on site. And most importantly, the technician must be fully trained, fully aware of what he or she is doing in the switchgear to do this test, and know when to say, no, we're backing out, it's unsafe. And I have done that. I was at a pulp mill and had to call all stop, simply because when we pulled the cover off, we actually were hit with a large amount of ozone because their switchgear was already breaking down for other reasons. So the technician that is doing this testing must be fully aware of all the safety precautions associated with doing this test.
Good, good. Yeah, and another safety precaution is that people don't necessarily keep in mind is the ground strap itself has to be adequate to carry any amount of fault current that might be generated from a phase to shield fault. You don't want to put an RFCT on the ground and then have the ground separate because of a fault. It's very unlikely, but it's a very bad result. So make sure your grounds are good, solid, and certainly heavy enough to carry any expected current.
Bill, if I can add one last thing. We were brought in to do cable testing, online cable PD testing after power up, which was a little bit unusual, but it was the way they specified it in their design specifications. Was instead of doing over potential testing of any kind, they said, okay, after we power things up, we want to do partial discharge testing, and it'll be online. And I went in with the radio frequency CTs. The problem was the installer actually failed to connect the cable shields to ground. So when we first opened it up, we had to come to a complete stop because the cable shields were just hanging out in open air. Wow. Those of you that are not familiar with cable shields, they develop one healthy charge, and it is a life safety issue. We immediately had to stop work, back up, and notify all employees involved of this safety concern. So before you start any of your work, you need to safely evaluate, are the working conditions safe enough for you to continue? And lastly, in the instruction manuals with the various components that we've had the opportunity to use, one of the things it clearly states, hazardous potentials exist on the shields.
Yep. Okay, next question, and here this brings up the sensor you were talking about, Tim. Jeff, you want to walk us through these different types of sensors?
Yeah, okay, so let's go through some of these sensors, guys. So we use different kinds of sensors to detect different kinds of PDs and PD types and in different components in power systems. So for example, you look at the RFCT there, or they call the radio frequency current transformers, RFCTs, HFCTs, they are all the same, but different manufacturers or different folks use different terminologies. Hopefully they'll settle down with one and move on. So they are typically used for cables. But having said that, that's not the only sensor that are used in cables. You use the TEV, especially for if you are in the switchgear environment, you want to make sure that you can use the TEV and ultrasonic to confirm whether the terminations are good. And as multiple in the last few NETA, if you go through the NETA papers, that most of them talk about PDs. They talk about 60% of the failures in cables are predominantly due to the failures in terminations and joints. So just to recapture, so although we use RFCTs for cables, we also use the TEV and ultrasonic sensors for the terminations. Now, having said that, the ultrasonic mics that you've seen here, those mics are used for, they have a center frequency of 40 kilohertz. They're typically used for surface discharge, detect surface discharge. But then the TEV sensor, I don't think it's here. Or is it? Is that the one?
The one on the lower left is a monitor TEV.
Yeah, no, that one is different. That's actually a capacitive-based sensor. It's used for transient earth voltage detection. The RFCT is about 20 megahertz bandwidth sensor, which measures charges in picocoulomb. And the dish type a little more sensitive than the ultrasonic mic. The dish type, the parabolic type ones, they are mostly used for outdoor environment. Insulators, overhead lines, but definitely can be used in switchgear, especially as Tim mentioned, when the doors are open, you want to stay in a certain distance and be able to locate the PDs. The contact probe is sort of non-directional, highly sensitive ultrasonic sensor. It's pretty much used as the last option if you don't have any air gap to use the other ultrasonic sensors.
Okay.
Yes, I covered all of it.
Yep.
All right, here's another question we get all the time. How often should I do it? As if there's one answer. Stuart, you want to tell us how often we should be running our tests?
If it was up to me, we'd all have 24/7 monitoring, but that obviously is expensive to be doing 24/7 monitoring on all our HV assets. So generally, it comes down to risk. So how important is that switchboard, and what is the consequence of the failure on that particular asset? So we have cases where failures have been undetectable with an ultrasonic microphone or at all, and then the switchgear has failed within 4 months of that test. And we've got monitor trends that prove this to be the case. So if it's a really important switchboard and you go, no, there's absolutely no chance you want it to fail, then you would need to do it at least every quarter, but then you need to really be considering looking at monitoring. As a general rule of thumb, if I own my own electrical network and I could go to the substation generally quite easily, I'd probably go every quarter. For customers who are needing to get a outside company to come in, then you probably want to be looking at 6 to 12 months to be doing your surveys. At the very minimum, the longest between should be 12 months between any PD survey I would recommend.
Okay.
The other thing I'd like to add in, though, with regard to that is look at your environmental conditions. And there are certain times of the year where your humidity and conditions are more, would potentially contribute more to partial discharge occurring. If you did it in 22 degree, or not 22 degree, but low temperatures, low humidity, partial discharge may or may not occur. or be occurring.
Right, and then good segue into the next question, Tim. Also, if you're in a high humidity, high salt humidity environment, more often is better than less often. If you're in a very dry location, you might not need to do it as often. So the question is PD continuous or is it random? Well, as it starts, I mean, it depends on the type and the exact severity and the conditions, but PD can come and go over time. It can come and go with voltage. It can come and go with load even. Typically, it's not very load related, but certainly you may have PD that starts at or above line voltage, and if the line voltage drops, it may go down a little bit or stop happening. You may have high humidity environments where it's hot and humid in the summer and it starts, and then you go to the dead of winter where it's really low humidity and it stops. So it does come and go, but it doesn't go away on its own. You know, it's eventually going to get humid and it's eventually going to come back. Okay, for Tim, so I've got some PD damage on my insulator. Can I just clean it off and go on my merry way?
I would like to say yes, that'd be wonderful, but in fact, this particular picture attached was from a facility that had had it previously repaired. They actually tried to patch over, and again, it just burns. And if you look at it, this is a particular section of bus bar that came out of a powerhouse, and it's eating away not only at the insulation. You've got tracking that's occurring. You don't know how deep it's getting, and to try to just patch over it does not fix the root issue. You still have, because it's tracked in two different directions, first at least two different directions, and all seeking ground or the opposite phase. In this particular situation, you have bus damage, and this is called a fluidized type insulation. Basically, it's a liquid insulation that's molded around the bus bar. And once that stuff is damaged, it is really not recoverable. The molded or red glastic insulators are gray, sometimes they're black. Same issue. Once the damage starts, they're very, very hard to recover. And your best option is to always get in there and do a permanent replacement. Let me add one last thing, and this goes back to the old timers. A lot of the boots, in this case, the very first boot that was shown at the opening of this session, a lot of damage to it. Exactly. The old practice of using duct seal or nep seal, wrapping it with a combination of varnish tapes or fiberglass tapes, followed by rubber and all of that, it eliminated air. And remember, when you have the ability to eliminate air, you have already started to remove one of the methods of tracking. So I realize we've gone to modern connections and modern termination processes with the boots and stuff like that. But I think the old timer, personally, I'm starting to think the old timers knew the best way to do it, which was to use the nep seal or duct seal and the varnish tapes, the fiberglass tapes, and all of that.
Okay, great. We're about halfway through our questions, just to let people know we're moving on. So how are the partial discharge magnitude and pulses per cycle? So these are two things that are measured when you take an online measurement, typically a TEV measurement, and you've got, well, are pulses per cycle important or is amplitude important? Well, if you imagine that you start out and your pulses are occurring only on the positive phase and a positive half cycle, and then maybe they're only occurring every 2 cycles. So now you've got a half a pulse per cycle. As the damage progresses and the voids get bigger, you get more and more pulses. You get the ability for it to discharge, charge, and discharge again within a half cycle. And maybe that's happening in positive, negative. Now I'm up to 4 pulses per cycle. So the pulse per cycle count actually does contribute to your knowledge of how severe it is. It's a combination of amplitude and pulse per cycle. Now, if you go into 10 or 20 pulses per cycle, that's hard to do with an internal void. So that tells me that it's probably surface discharge. 2-3 pulses per cycle might be internal, 10-20 might be surface, 600 pulses per cycle means I'm listening to the cell phone tower down the road. So within ranges, the pulse per cycle count can help you determine what you're actually listening to. Okay, so the next question is infrared. We have a lot of customers that say, well, I do infrared testing. I have to do that every year. And since PD generates heat, won't that locate the PD for me? Jeff, you want to answer that?
Yeah. This is typically a question I get asked regularly. Hey, we've spent all this money on having these cameras, and why can't we use IR cameras to pick PD? One thing that I want to make it clear is that heat and the IR cameras are used, and they're based on the load. So the system has to have a load for IR camera to work, compared to PD is mostly voltage based. Having said that, typically if you look at the overall power systems, 80% of the failures, especially in medium and high voltage, are due to insulation breakdown, and significant amount of that starts as a PD. The challenge you have is the whole purpose of the detecting using these various kinds of sensors to detect PD is to being able to detect the PD way ahead at an incipient level, so that we can take precautions. At the initial stage, PD doesn't emit a lot of heat, and that's why typically we don't recommend using IR cameras, which is heat sensitive, to use to detect PD. So that's the key. Especially and when heat becomes a factor, what you have is it's already the insulation is significantly damaged. So if you ask me, infrared detection is not the best methodology for detecting PD.
Okay. The number one question we get after is it voodoo or is it not voodoo is, okay, I've got PD, when's it going to fail? Tell me down to the hour, minute, second that it's going to fail. And what do we tell people when they ask that question? Stuart.
If we had the answer for that, then we'd all be quite rich, I think. But yeah, about as easy as the lottery. But we generally, there's a lot of things we can take into account when we determine the time to failure. The type of PD is a big starter of that. So if it's an internal void type discharge, so we're looking for an internal void within the insulation, and that's breaking down, and it's going to be getting larger as each cycle goes through. That tends to trend a lot over time, and it will, so we would generally trend, so transient earth voltage, internal void type measurements, we would say over a longer period of time, it's a longer time to failure. A surface related partial discharge, I think if we detect any surface related partial discharge, we generally recommend intervention as soon as possible, like similar to what Tim was saying earlier. We found this problem, we can see a track on the outside of there. We want to try and turn it off as soon as possible, because generally it will lead to failure in quite a short space of time, and the more damage it does to all the surrounding components, along with corona type discharge inside switchgear, will cause an acidic atmosphere. So the longer you've got that acidic atmosphere, the more damage you're doing to all the components within that compartment. So we would recommend that we try and intervene as quick as possible on that. And similar with cables, so for cable PD, we have two major types of insulation. There's a polymeric insulation and there's a paper insulation. I know the US hasn't got a lot of paper insulation these days. The UK has still got quite a lot of paper insulated cables, but paper cables generally have a lot of active PD in them, and we can trend that again over time, and when they reach certain thresholds will give us an indication. But polymeric insulation, we would recommend a lot sooner intervention again, and if it's in the core, the location of the PD. Again, environmental environment will come into that as well. So sometimes we can improve the environment in the substation and again extend the life of the asset. So if we're getting only getting ultrasonic when it's high humidity, we might be able to install a dehumidifier, things like that, to try and extend that time for us. So, okay.
Great, thank you. Yes, we've had many customers install dehumidifiers just to extend the problem.
Yeah.
So VLF, well, VLF is a PD-based test that's done offline, and it works, and it's a great test. So why don't I just do that? Jeff, you want to answer that?
Okay, so this is I spent quite a bit of time on the field services side, or the service side, electrical high voltage service side in the past few years. I'm familiar with the situation, and I'm also seeing how things are changing continuously. If you ask me if it is a yes or no answer, the answer is it's if it is an option between to have the online PD detection versus doing a VLF, I prefer the online, just for simple reason is that nowadays the companies, the plants are trying and figuring out ways to extend the turnaround period. Years ago it used to be every 2-3 years. Nowadays I see already it's moving to every 5 years. And PD, sometimes the PD from initiation to catastrophic failure could happen within a few months. So waiting and doing a VLF test every 5 years or every 3 years may not be enough. And so nowadays with this current technology, with non-intrusive sensors, it's a lot more easier. You don't need an outage, and you can scan very regularly. I typically advise the clients, hey, they do already have an IR scan schedule, which is typically every year. Why not do the PD scan at the same time? So that means you are scanning every year, and you're not spending too much resources because you can train the same folks who are doing the IR scan to do the PD scan, and so that clients can extend their turnaround schedule, from 3 years to every 5 years without much of an issue.
Okay, thanks, Jeff. All right, so we should be cleaning our switchgear regularly when we do have these turnarounds. And what happens when we use the improper cleaning materials, Tim?
Okay. First of all, any of your cleaning products that are out there must be appropriate and approved for electrical service type work. In other words, it can't be anything that'll break down or leave a residue. In one case, I was at a lumber mill, and I got pulled aside by the sawmill foreman and brought over there, and they were in cleaning their own switchgear. And it turned out what they were doing was, after they were cleaning the switchgear, they then applied a layer of car wax, and to clean them up, polish them, and theoretically seal the molded insulators. And I'm going, what? And my eyes got real big. And of course, luckily the equipment was shut down, and you could see the partial discharge damage. And it was very evident, and we scheduled another shutdown with them. This particular shutdown was their own maintenance period. I just happened to be on site doing other work. But we came back 2 weeks later and replaced all the insulators and installed heat and all of that. So cleaning materials must be approved for electrical work, is what I'm trying to get at. Because moisture is absorbed into the insulators potentially. There could be conductive materials in the material that you're using, or leaving a residue. Good products like the old-fashioned 409, where you went in and, hey, it was great for degreasing things. The problem was it left an ionic residue. So again, I can't stress this enough. Make sure you're looking at your cleaning products to make sure that your rags are lint-free, so they're not leaving material behind. And more importantly, any chemicals that are used are approved for electrical work.
Great. Okay, so there is another product out there that some people use. It's a Corona camera, and it basically uses detection in the ultraviolet range to see corona discharges in the air. How would you compare that with using ultrasonic or UHF-based detection, Jeff?
Yeah, so again, first and foremost, corona cameras, or also known as UV cameras, ultraviolet cameras, they're extremely expensive to begin with. Typically, transmission line companies, they own them, and they're about 5 or 6 times the cost of a typical PD detection set. And then on top of it, the use I have seen, some of these manufacturers claiming that they can detect PD. But having said that, the usefulness is limited. For example, yeah, it can detect PD, especially surface PD, if it is visible. But on the other hand, the challenge is it cannot differentiate from corona to surface PD, and that's one. And then on top of it, the application is mostly for outdoor gears. If you get into the indoor gears like switch gears, cables, then the camera is not, its use is limited. So that's why pay more and get less. I mean, don't get me wrong, the UV cameras have their purpose, but detecting PD is definitely not the main one.
Okay, thanks, Jeff. So, Stuart, sometimes we talk about doing full-time monitoring, sometimes periodic surveying. Why would I go to that extra expense of doing full-time monitoring?
Well, there's a number of things that you gain. Obviously you got the full-time monitoring, so we can see intermittent discharges are a big one that a lot of our customers have got. Is you can pick up discharge sometimes, and then other times of the day, so like you say, humidity and things. The monitoring systems will monitor for humidity. Obviously, the criticality of the switchboard is the main thing. Prolonging asset life as well. Some of our customers have got monitoring systems that, the substation was installed 20, 30 years ago. Now a lot of buildings have been put around it, things like that. Trying to now change that switch gear out for a new switch gear, is getting towards the end of its life, is a big job. So instead of doing that, we can install a monitor and really lower the risk of the switch gear failing. So if we've got a monitor on the system, we can actually indicate the condition of your asset. That's the key thing that we're getting with having a monitor on. We're getting a condition of the switch gear, rather than just, it's 30 years old, so I'm looking to replace it, or 50 years old, I'm looking to replace it. Also, staff safety. If you're going to be entering a substation, the more information you've got and in that kind of environment, the better it is. So we have customers who install the monitor and they'll check the data for 2 or 3 days running up to when they're going in the substation. They'll check the last 2 or 3 days worth of data and make sure that there's been no evidence of PD in that time. So it just gives them peace of mind as well. And obviously we can reduce the cost of future maintenance by having the condition of the asset at all times.
Great, thank you. Okay, we touched on this a little bit, but Jeff, can you just quickly summarize the difference between these 4 sensing technologies?
Okay, so I think I kind of partially answered this question before. The transient earth voltage is typically used to detect internal PD, especially if you have an insulator with the void, and if they're not visual. TEV is the way to go, but it can also help to determine with some intelligence built into the device. You can also determine whether it's actually internal or sort of external, and then you can use if it is surface discharge, you can confirm that using an ultrasonic device. The ultrasonic devices, since most of the PDs or the prominent PDs are related to surface PD, I would suggest that you start with ultrasonic and then work your way through. UHF is definitely interesting. You know, in the past, my experience with them is using them in the outdoor gear, and as I mentioned, this helps to separate corona versus actual surface PD. And the RFCT is mostly for cables. And one thing that I've started, and I'm happy that the clients are eventually moving towards permanently installing these radio frequency CTs. So, because in the past, I have seen clients using the transient earth voltage, the ultrasonic sensors, and they check their switch gears and their outdoor insulators and being happy with it. But as you know, typically your weakest link it will eventually be your cables. So having, and sometimes the safety requirements restrict them from being able to open the switch gear and install the RFCTs. But if you can permanently install RFCTs, then when you're doing your the yearly ultrasonic or PD scanning, you can also check your cables.
Great, thanks, Jeff. So I get a TEV reading, and I've got 3 cabinets in a row, and they all give me some TEV. So I'm hoping I can just go to the highest level, and that's where the PD is actually occurring. Is that the case, Stuart?
And no, it's not the case in all situations. So it depends on the propagation path from the source to where you're picking up the signal. So we can actually end up with a higher amplitude signal on the adjacent panel or adjacent area of the switchgear. So the best way to actually locate where the pulse is coming from, so the pulse emits a signal, induces a pulse into the switchgear, and that starts to travel on the surface of the metal on your switchgear. And by using time of flight, so we have 2 sensors, one that's built into 2 sensors, 2 TEV sensors, and we space them apart on the switchgear. It will tell us which one the pulse hits first, and then we can determine which direction it's coming from, and then we can get that down to around about 15-20 centimeter, so we can easily identify which cubicle it's coming from, and normally front to back, whereabouts in there. So it's a good way to get started. A lot of time, as Tim said earlier, you'll still need to then open it up. And for an internal void, quite often that might involve removal of a component and double checking if that is the component that's got the failure, because there's no, for an internal void, there will not always be a visible, on the outside problem. You look at it, it looks like the day it's been put in, but inside is the problem. So so we can use time of flight to actually determine where the signal is coming from within the switchgear.
Great, thank you. So there's a lot of devices out there for doing ultrasonic measurement. Ultrasonic guns are made for vibration analysis and air leaks and vacuum leaks. Why would I not just use my general purpose ultrasonic gun to find PD? Stuart?
Well, the main advantage of using a PD determined ultrasonic sensor is it's already set up in the perfect frequency range. So our instrument is set around 40 kilohertz, and it gives the best measurement for PD rather than having a wide band ultrasonic. The ultrasonic range is a wide area, and so we want to try and identify the exact area. Also, it's tailored, and we can have classification and things like that of the sound with our instrument. We're totally used to listening to for PD with the instrument, so it's not a general purpose device. Our instrument on the screen will actually show you there and then that it's PD. It's not, you don't have to do any further investigation afterwards or setting of gains and frequency levels and all that type of thing. That's already set for you on a PD directional antenna, microphone.
Yeah, it's worth noting there's a lot of things that give off ultrasonic energy, whether it's a clothes rustling or vibrations from different things and background noise. Discriminating between what's a high level ultrasonic energy, not electrical system related, and what is electrical system related is one of the harder parts. And 10 years ago, 20 years ago, you had a calibrated ear, And now the more modern instruments give you a lot of tools that teach you or help you discriminate between noise and PD. Okay, Tim, briefly, I mean, this topic could be a webinar into itself, but the impact of maintenance programs and other atmospheric conditions on deterioration.
Okay, let me real quickly, as a background in this particular, this is actually low voltage. We also have found the same breakdown inside medium voltage switchgear, and this is a combination of chemical and atmospheric environmental conditions that literally was breaking down the external jacketing on CTs. In this particular situation, this was at an old Amoco BP petrochem facility. I was at a DuPont facility that had similar issues. This was found around 2008, but basically the insulation. So a combination of things. Had this been medium voltage, would this have shown up on partial discharge? Potentially, potentially not. In this situation, though, if you look, your phase CTs, and this was just for metering CTs, look at the gap. Now, had the insulation completely melted off, now you're talking about a phase-to-phase bolted fault between the two phases, simply because the internals of the CT are fully contacting each individual busing, and the gap between the two CTs was less than a half an inch. It would have popped across and blown up. So it's extremely important in your maintenance programs that you get in regularly. And it's been previously mentioned both by Jeff and by Stuart, the criticality of the equipment really comes into play, how often you get into your switchgear and do your inspections, both from live online inspections, whether it's doing partial discharge and infrared and other testing, to doing normal shutdown routines where you're getting in doing further invasive testing and inspections. This could have been a very catastrophic failure is what I'm getting at.
Yeah, so in addition to worrying about heat and humidity and salt air, we also have to worry about caustic chemicals that may be given off by your process or used by your process, damaging insulation.
Waste treatment facilities, a lot of, sulfur dioxide is released. It's pretty common there. That eats away at the silver jacketing or silver plating on busing.
That's right, that's right. Okay, so this is the last question, and it's a very common question that customers want to know, what standards should I meet? What standards should I be testing to? Well, what is there? Well, there's actually very few. In North America, we have the MTS, which is an ANSI standard all put out by NETA and just revised last year. This covers the maintenance and testing of switchgear. Does not cover cables, but it does talk about switchgear. There is no good standard in North America for field testing of cables for online PD. There's some, the IEEE 400 series does a lot of offline testing, but it doesn't talk about online. Internationally, there's IEC 60270, which has been around for a long time and is for the online testing for PD for both switchgear and cables. It describes test equipment standards and all that. It has an annex that talks about what they call non-conventional methods, which are things like we've talked about today for ultrasonic and TEV and UHF and those sort of things that in the 60270 world would be considered non-conventional because they are not direct connected. 60270 requires a direct hardwire connection to the conductors. So that's our questions that people submitted ahead of time. Do we have any questions from the attendees? And I want to point out that our time is officially up, but there is no hard end time. We will sit here and answer questions as long as you have any questions. So Tim Irwin, you want to let me know if we got anything? See if you
we have 4 questions right now in the queue. I'll just take them the order they came in at. First one, we are using EA Technology UltraTev Plus 2 kit. So we are getting PD values in dB millivolts, pulse per cycle, and severity. What does the severity mean?
Okay, I'll take that one. So severity is a number that we invented. As I pointed out in the section where I talked about the TEV amplitude is important and the TEV pulse per cycle number is important. Severity is a mathematical combination of those two, where we've tried to put a single number to tell you how severe the discharge is. It's good. It's there a lot for legacy reasons. Now you've got pulse per cycle and you've got the actual TEV amplitude. It's better to keep track of both of those. Severity is nice, but it's better to have more information and not a mathematical combination.
Yeah. I mean, it's like Bill says, from a legacy product, and really, you know, your PRPD gives us a really good indication of these types of things now, and I think there's a way of classifying that kind of thing. So really, phase resolve plots, your amplitude and your pulse per cycle are the key ways to be identifying PD these days.
Okay, next question. What is your opinion regarding PD and detection of air insulated metal enclosed switchgear? The reason for this question is that a customer detected levels of PD in the yellow area that was detected with the help of the UltraTev Plus 2. And the international IEC standard 62271, it clearly stated that it is not yet possible to establish a reliable relationship between the results of PD measurements and the life expectancy of the equipment due to the insulation system used in metal enclosed switchgear.
Anybody want to jump in on that, Tim? If not, I will.
I guess from my standpoint, if you're using, and again, I'm not product specific, but if you have a method of detecting partial discharge, I can't stress it enough. It is just like getting in and doing an infrared scan where you find a hot spot. If you suspect that you have partial discharge, it now puts you in the driver's seat. All right, correlations and you know, having done this now for several years, and I'm just like Jeff and yesterday when we were chit-chatting about this, where he said it was voodoo. When this first started, to me, you know, voodoo is one thing. This is smoke and mirrors. But what I'm getting at is that we have now found true relationships between locating partial discharge and actual damage. And frankly, if you suspect you have partial discharge because you are using equipment and certified and regularly maintained properly good test equipment for the purpose of locating partial discharge, I can't stress enough. It puts you in the driver's seat of determining, and there is no correlation between detection and failure point again, because it could get worse rapidly. It puts you in the driver's seat so far as making decisions about courses of action and repairs and further detection, first of all, locating it. Does that answer the?
Well, I'll add on to that, Tim. You know, there may not be a correlation says I've got this level, therefore it's going to fail in 6 months, because it varies quite a bit. And
Exactly.
it also, if I have this level, I should take action now. There's no correlation, because if you have a fully redundant system and you have a turnaround coming up in a year and you want to live with that risk until you can repair it correctly or appropriately, that's your decision. As opposed to, I have this one feeder, it's feeding a process critical system that is going to cause damage if it goes out, and I don't have a turnaround scheduled for 5 years. Regardless of the level, that risk might lead you to believe that you should do something right away. So it is a decision. It's based on a lot of factors, and there may not be a mathematical correlation between 37 dB TEV reading and failure 4.2 months from now, but it gives you information and lets you make informed decisions.
Yeah, I mean, it's someone who spent quite a bit of time on the other side of in the service sector. It is very important to know the condition of the equipment, and I always tell when people ask similar questions, hey, it's like your transformer oil, DGA. You see an elevated level of hydrogen. What do? You know, can you live with it, or you can't, depending on the amount of the hydrogen the change of hydrogen level in your transformers, and also the criticality. Can it wait? So those are the decisions that you need to make. As Tim mentions, once you are aware of it, then it's up to you to make that call depending on the criticality of the equipment, which is is it important for your process, or can it wait? At least you're aware of it. So next turnaround, you will look into it once you take a shutdown.
Okay. Which is the best way for collecting PD information in SF6 isolated cabinets?
Okay.
Stuart, yeah, why don't you address that?
Yeah, for SF6 switchgear, it depends on the type of the level of the pressure of the gas. So if we've got GIS 130, 250 kV type gear, that's a different setup to a normal medium voltage SF6 equipment. So we're generally concentrating on that type of equipment in this. So it'd be medium voltage. So the best place for the mainly you're going to get TEVs. You're not going to get very good ultrasonic signal, obviously, because you've got no air path directly into where there could be an ultrasonic or surface problem inside your SF6 tubes or switches or any of those parts. So most of the time we use TEV on the cable terminations or any area that's got an insulated band. So where the joints meet as well, if there's insulation at that point, then the signals can get out of that point. So transient earth voltage signals do not go through steel, where they actually go along the surface of it. So they need somewhere to get out, and it needs to be an insulating material, whether that's air or polymeric or things like that. So cable terminations, put the TEV probe on the outside of the cable termination where it comes out the switch gear, and any kind of band joints along the tube. So, but obviously ultrasonic's a bit more difficult. Generally, we concentrate on TEV on that type of equipment.
Okay. How about the recent development of ultrasonic imaging from some well-known instrument OEMs to visualize the sound activity around the surface of HV equipment? Can they differentiate between surface PD, corona, or noise?
I'll take that one. We're familiar with those systems. I've seen them. I've played with them. They're great for finding air leaks and things like that. They work incredibly well. I actually used one to find a cricket in my house because I had it home and I couldn't find a darn cricket. A little expensive for that. But the problem with using them for electrical is their sensitivity is not as sensitive as a parabolic dish. You can't put a parabolic reflector around it. So looking at stuff from the ground from some distance, you've got to have a very high level. They're also not going to differentiate between surface discharge and corona. So you're not going to be able to find that. You're better off with a perhaps a UHF, a directional UHF device, or a parabolic microphone arrangement to look at stuff from some distance. If you can get pretty close to the gear, it's a very interesting tool. One issue with it is if you're looking at gear that you can get close to, it tends to be metal clad, and that's not going to buy you anything for that. But I view it as a add-on. It's another tool in your toolbox. It won't replace the handhelds that are designed specifically for PD. But if you have a particularly nasty problem where you can't figure out which phase you're dealing with, and it's a high-level source, it makes a very interesting tool.
All right, this one's a measurement specific. If I got 12 dB millivolt PD value in an UltraTEV Plus 2 kit, what does that mean? The dB millivolts.
dB millivolt is the amplitude of the pulse. So TEV, we actually measure the height of the pulses that are traveling on the surface of the switchgear. And it's a logarithmic scale, which is a dB, and then it's in millivolts. So the 1 dB is 0.1 millivolts, and 60 dB on our instrument is a 1 volt pulse. So 12 dB, somewhere in between. I don't know off the top of my head on a logarithmic scale, but it'll be. So that's what we're measuring. That's what it means. In regard to PD, it's quite low. We know we would generally go into the amber range at 20 dB and then go red media investigation at 30 dB or 29, 30 dB. So it's not a high level. And obviously the first thing to identify is that it's definitely PD. So you need to check your phase resolve pattern and see if it's actually 180 degree clusters and things like that. So it's a low level measurement on our instrument.
I'd like to add to that, and Stuart hit it. And early on, when I was doing, I found, and I was very, very excited. I found something. I knew I found something, and I sent it off to Bill, and he says, "You did not lock it in so far as your phase, phase resolve or phase lock." And it's like, oh crap! It's critical when you're out there, and yes, you have a reading. But as Stuart mentioned, you've got to compare it to your phase relationship to find out where it's occurring in the half cycle. If you're not doing that, it really is, fortunately, useless information. It really needs to have resolution between where it's occurring in the phase cycle. Otherwise, you get schooled and you go, okay, oops, I may have had something, is what it turns out.
How do we segregate the TeV magnitude in millivolts from dB millivolts? This comparison between TeV readings and the ultrasonic reading.
There's no relation between the readings on ultrasonic and TeV. They're two totally different animals. TeV is a measure of the actual voltage that appears on the switchgear, and that voltage is dependent on the high frequency impedance of the ground system, which is not something that's controlled. So the TeV amplitude is very much an electrical phenomenon, whereas the ultrasonic, even though they're both dB, that just means we're using a logarithmic scale for both. That is the sound pressure level. Ultrasonic is a sound pressure that is traveling through the air and through the solids, and it's the actual output of our sensor. It tells us how loud the sound is. And so there is no relation between those two measurements.
And the last one that's in the queue right now is more of a statement. I think, Jeff, going back to what you were saying about the transformers and the dissolved gas, the transformer statement is vicious. Those levels are quantifiable and show that something is happening inside a liquid-filled winding or component. PD levels don't have that ability at this point. PD shows there's an issue, but is not able to pinpoint severity.
Well, I'll address that. Yes, VGA has been around a long time and is perhaps a little more scientific in that there's more information, but certainly a TeV level of 30 is worse than a TeV level of 15, and an ultrasonic level of 25 is worse than an ultrasonic level of 5. And while there may not be a direct correlation that a 25 means that it's going to fail in the immediate future, we've determined thresholds, and these thresholds are given in the NETA 2019 standard that says if you have a level above X, you should take action immediately, or you should take action at some point when it's convenient, depending on the level. So there's a lot of history and tens of thousands of measurements being taken around the world over the past 20 years. And those are not so much empirically, but they're used to determine thresholds of when you should be doing things. So there may not be a hard, fast scientific correlation, but there's a lot of experimental information out there that's given us these thresholds in this relation.
Tim, if we can step back to that question, though, it was DGA issues versus PD. Is that correct?
I believe when Jeff was talking about that original question, he mentioned similarities with doing a dissolved gas analysis and seeing hydrogen in the oil as compared to seeing PD present in switchgear and basing your future actions on that.
No, what I
Oh,
mentioned
okay.
is,
All right.
I think, just to correct it, what I mentioned is the thought process. When we see when we see a bit of an elevated hydrogen level, we don't shut the transformers down right away. Likewise, when we see a phase resolve plot, when we determine there is PD, what we do is we start to narrow the focus. On transformer case, we started to monitor them regularly. Instead of doing every year a DGA, now we start to do every 6 months, every 3 months, making sure that it's not going beyond. So it's the same thing. When you narrow it down on PD, you want to make sure that that you're focusing on those equipment that the failure doesn't happen and leads to a catastrophic failure. So that's what I meant. The focus narrows down.
And Jeff, if I may,
Yeah.
I think part of it is when you detect it, it may not give you an immediate, we have to shut down in X amount of months, but you can now start to trend it over time.
Yeah.
And retest it and see if it's changing, see if it's varying, going, if it's a critical circuit to full-time monitoring, something to that effect, trend it over time once you identify its presence.
I'd like to add, I've got a very good example, and this one is was a transformer. All right. It was at a refinery. It experienced a through fault. Basically, they had a fault downstream of this transformer, but it actually damaged the tap changer. All right. And they knew exactly what had happened, and they started to closely monitor the transformer and take regular oil samples, and they noted the rise in DGA combustible gases. Ethane, methane, those gases were going up. Okay. And it allowed them to extract continued service out of the transformer till it became too dangerous. And the analysis said, shut the transformer down. But they were able to continue the production at this particular refinery on this particular circuit for a significantly longer period. But they were doing monitoring. So if you equate that to partial discharge, is once you've detected it, now you need to begin, as Jeff has said, as Stuart has said, is to monitor it and start to trend it. The monitoring could go anywhere from, okay, we're going to do it every month or 6 months, down to a shorter period of time. But we've stated it previously, there is no direct correlation between this level and ultimate failure. So you start to have to make some serious decisions. When do you shut the equipment down to repair it?
And that looks like the last of the questions that were submitted. And I don't see any hands raised.
All right, well, I want to thank everyone for sitting in and listening. I think we covered a lot of information, and some of our answers you may agree with or disagree with. If you'd like to argue, feel free to shoot me an email, and we can argue points, and I can get you in touch with the other experts. But I appreciate your time. We will be putting a copy of the presentation. We'll send to everyone. And we will also be putting a copy of the video on our YouTube site as soon as it's processed. So within 48 hours or so, you should have this information. Feel free to pass it along to anyone else that would like to learn. And if you have any more questions, feel free to contact any of the four of us directly. Thanks, and have a great day.
Thank you.
Bye-bye now.
And the presentation.